In this fourth segment, we're going to study how quantifiers, logical connectives, and variables fit together into this new system of logic called predicate logic. So predicate logic is nothing but propositional logic extended with two things. First of all, we have variables and predicates to represent the subject and the verbs or the verb phrases of our propositions. And second, we have quantifiers to quantify over the variables. And that's it, that's predicate logic. Now, the first thing to realize is that predicate logic quantifiers have precedence, like the logical connectives, and that their precedence is the highest one. In other words, if you write for all x, p of x, and q of x, then the precedence for all x is higher than the precedence of conjunction, which means for all x goes with p of x, not with p of x and q of x. That's what the precedence means. And similarly, the existential quantifier also has a higher precedence than the logical connective, so there exists p of x and q of x. If you write it like this, by default, the precedence of this quantifier is higher than the precedence of the conjunction, therefore there exists x only applies to p of x. So are these two expressions here propositions in predicate logic? And the answer is no, for the reason we just explained, namely that for all x has a scope that stops after p of x, which means this x, this variable here, is not in the scope of for all x, and therefore its value is left unspecified. That is unacceptable, and therefore this expression is not a proposition in predicate logic. And for the same reason, this x doesn't have a specified value either, since it's outside the scope of this existential quantifier. So for the same reason, this expression is not a proposition of predicate logic. So now it's time to enter into a new binding contract, that is to give a new definition. We say that a variable is free when it does not appear within the scope of any quantifier. So for example, the variable x here in q of x is free because it does not appear in the scope of any quantifier. It doesn't appear in the scope of this one, and there's no other quantifier in that expression. On the other hand, this x is not free because it appears within the scope of this quantifier, and we just argued. And when a variable is not free, we say that it's bound. So a variable is either free or bound. This one is bound by this quantifier, this one is free. And similarly for the second expression here. So with this definition of a free variable now, it makes it easier to distinguish what's a proposition and what is not. In particular, the reason that these expressions are not propositions is because they contain at least one free variable, that is, a variable for which the value is not specified. So the important point here is that by definition, a proposition may not contain a free variable. If I give you a syntactically correct expression of predicate logic with no free variables, then it must be a proposition. Now let's consider one of the expressions we had on the previous slide and try to convert it into a proposition of predicate logic. We're going to discuss two ways of doing that. Remember, this expression is not a proposition because of the presence of this free variable here. So the first way to get rid of the free variable is to add parentheses to the expression to explicitly define the scope of the quantifier to include that occurrence of x. So by putting parentheses here around p of x and q of x, we make the scope of this quantifier extend all the way to the end. And therefore now, this is a proposition, let's call it P1, because it does not contain any free variables. Just realize that both this occurrence of x and this one are bound to the same quantifier here. Now let's go back to our original expression, and another way to get rid of this free variable is to make it appear within the scope of another quantifier that we can insert right here in front of q. So instead of adding parentheses, we could add a new quantifier, say an existential quantifier. And let's call P2 the resulting proposition that reads there exists x p of x and there exists x q of x. Now that we obtained two distinct propositions, P1 and P2, from the same expression here by trying to remove the free variable x, it's natural to ask the question whether P1 and P2 are logically equivalent, meaning, do they always have the same truth value? Are they both true or both false? We're going to answer this question using our pictorial representation for these propositions. Remember that we always start by drawing the universe as a rectangle containing all of the possible values for the only variable here, namely x. And now we have to draw the predicates p and q to answer the question. I will let you think about this problem for a while, so please pause the video and start it again after you have figured out the answer to this question. Now it turns out that if the answer to this question was yes, you wouldn't be able to prove it using a single picture. Because by drawing a picture, you're not actually considering all the possible cases to convince yourself and everybody else that these two propositions always have the same truth value. So you couldn't prove it if the answer was yes, or you couldn't use that pictorial representation to prove it. So it turned out the answer is no, these two propositions, P1 and P2, are not logically equivalent. And you can use this pictorial representation to prove that, because all it takes to prove it is to come up with one counterexample, and that you can draw in this picture here. So the goal of this exercise now is to find a way of representing P and Q such that one of these propositions is true and the other one is false. So since you've thought about it, hopefully you came up with this counterexample. We're going to draw P and Q as follows. P can be drawn anywhere, assuming it contains at least one element, like this one. And then we're going to pick Q such that this proposition, P1, turns out to be false. Now for that to happen, it must be the case that there are no elements in the universe for which both P and Q are true. And the easiest way to make that happen is to draw Q with no intersection with P, like this. There are no elements here that are both in P and in Q. Therefore, there does not exist an x such that P of x and Q of x is true. Therefore, P of 1 is false. All right, that's just one case, right? But what we need to check now is the truth value of P2 in this particular case. Well, for P2 to be true, it's a conjunction. We must check the truth value of the first operand, which happens to be true, since there's at least one x in P, and then the truth value of the second operand, which is also true because there's at least one x for which Q is true. In other words, this conjunction is true, which means that P2 is true. And since we came up with an example or a situation where one is true and the other one is false, clearly those two propositions are not logically equivalent. So be careful. These two approaches that we used to generate propositions from this expression. They are both valid ways of generating propositions, but they do not generate logically equivalent propositions. Before we conclude this segment, I want you to work on a similar problem. In other words, start from this expression here, which is not a proposition because of this free variable x, and then build two propositions using our first method of adding parentheses to explicitly extend the scope of the universal quantifier here, thereby obtaining the proposition P1, and to generate a second proposition using a second technique of inserting a quantifier in front of Q. And in this case, we insert a for all quantifier since that's what we started with here. So now we have two propositions, P1 and P2, and I want you to go ahead and pause the video and determine whether P1 and P2 are logically equivalent. So the answer again here is no, they are not logically equivalent. The easiest way to prove that is to come up with a counterexample. And here we're going to draw a situation where P1 is false and P2 is true. So we start with a universe of possible values for x, and then we start with the predicate P. Now to make P1 false, we need to make this conditional false for at least one element in the universe. That is, we must find an element in the universe for which P is true, but Q is false. That's easy. We can draw Q like this, where this element is in P, but not in Q. And therefore, for this element, the conditional is false. Therefore, P1 is false. Now, I want to convince you that in this case, P2 is true. P2 is true. Notice P2 is a conditional, so it's true if its premise is false. And what is the premise? Premise of the conditional says for all x, P of x. Well, is it true in this particular case that P of x is true for every element in the universe? And the answer is no. So this element is such that it's not in P. So P of x is false for this element. Therefore, for all x, P of x is false. And therefore, false implies anything is true. Therefore, P2 is true. Since P1 and P2 have a different truth value in at least this one situation, they are not logically equivalent.